Okay, last week we have discussed the derivation of higher order terms, which appears as the frequencies goes up. So as you can see here, for this parallel plane inductor structure, the derived EX3 terms is the third order terms, which can be verified by checking the expression of the term. As you can see, here is the omega to the cube. That's the third order dependence of frequency. And the electrical field, the EX3 terms also is depending on, it's also a function of position Z. And you can see as the order gets higher, the expression for the field becomes more and more complicated. And here is the fifth order term, EX5. And you can identify it by find out the omega to the fifth term. So here is a simple illustration of the fundamental terms and the so-called higher order terms. So because this structure is driven by current source, so the fundamental term is the magnetic field, Hy0. And if the current is time variant, it shall produce the EX1 term. So together, the Hy0 and EX1 term are the so-called quasi-steady approximation, which is enough to describe circuit behavior in the low frequency region. However, as the frequency goes up, you will see that the higher order terms such as Hy2, EX3, Hy4, and EX5 appears consequently. And they are so-called the beyond quasi-static terms， 就是超越这个准静态的这些高阶模态，那在电路学的领域的话，这些高阶模态是可以被忽略不计的，因为当频率不够的时候，频率不够高的时候，它们的效果是不会那么明显的，I guess you can see that the derivation of higher order terms can be continuous infinitely. So as you can expect it, the total electrical field on this structure should be an infinite series, as this slide suggests. It's you'll have EX1 term, X3 term, 5th term, 7th terms, 9th terms, so on and so forth. And if you check up the expression for for low order and higher order terms, you can see that they can be collected as this expression. So here is the common terms of the first three terms. Then the rest are put into the series. So the first term is omega square root of mu epsilon L, the length of the capacitor. And here's the third order term. Then here's the fifth order term. And the series can be identified as a tangent series. That is, if you collect enough terms, the summation of all those terms shall becomes a tangent. A tangent as a function, a tangent function as a function of omega square root mu times epsilon times L. And the coefficient here, the first one is 1/3, 2/15, and blah, blah, blah. So they are referred to as the binomial coefficient. Should be binomial coefficient, right? Or tangent. So it's a tangent series. So you can find out the so-called analytical solution for this series. This can be proved mathematically. The tangent, the series as the terms becomes more, if you collect more and more terms, you should approach a tangent series. And one interesting thing, or one important property about tangent function is that for tangent x, if x is small, much smaller than 1, or x approaches to 0, then tangent x shall approximate x itself. 你自己拿手机出来去按计算机嘛，假如你是1度，然后去取它的 tangent 值，应该是一个很小的数字 ，OK。好吧，如果0.1、0.01好了，你会发现它取 tangent 值之后，跟它本身是一样的，Alright, so providing that omega times L times square root of mu times epsilon is much smaller than 1 or is approaches to 0, then the one-term approximation should be enough. The one-term result, here you have only one term, EX1. This result should approximate a tangent function, providing that the parameter is small enough. Okay, so according to this property, we can conclude that the so-called quasi-steady approximation, or the limit applicable for quasi-steady approximation, the requirement for quasi-steady approximation to be true is omega times square root of mu times epsilon times L is much smaller than 1. So this is the requirement, right? And it's a little bit awkward to memorize this property. So, so let's check out this expression a little bit. Omega can be expressed as 2 pi f, right? And what is square root of mu times epsilon? I suppose you should remember that the speed of light is what? Is 1 over square root of mu times epsilon, all right? So this thing can be replaced with Vp, the velocity of electrical signal, or the velocity of electromagnetic wave propagation. Alright, so by substituting this relationship, you can further identify that Vp, the velocity, equals to what? The product of frequency and wavelengths. So you can further derive that the requirement becomes 2 pi L over lambda is much smaller than 1. Is much smaller than 1. And if you approximate 2 pi, what is 2 pi? It's about 6.2a, or blah, 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 okay? So if you substitute 2 pi as a 6, you will end up with the condition that if the size of your component, if the size of the structure is much smaller than 1/6 of an wavelength, then you can say that it's a valid condition for quasi-steady approximation. 所以这一页的话，你看到的是所谓准进场有效的条件，准进场有效的条件，也就是说你那个电力要够小，小到什么程度，我们才能够说准进场，准进场。举个例子来讲AC 电力的讯号是不是电磁波？是啊，但是你平常在看电源的时候，你会去管说它的电磁场效应吗？假如你今天是一个60赫兹的那个电力讯号， 为什么？为什么你们不会去管它？因为60赫兹的波长是多少？3乘10的8次方除以60等于500公里吧？哦，所以对于电力的那个60赫兹讯号，是500还是5000？500了，500啊，500。所以对于电力的那个讯号，它的波长其实是500公里。哦，也就是说，你今天的10公尺、20公尺，甚至从这里到最近的变电所，可能1公里吧。这1公里占500公里这个波长的几分之几？小于360分之一嘛，小于360分之一个浪达。所以我们说，从台科大到最近的变电所，哦，假如发生停电啊，或者是电力不稳的什么现象的话，它所造成的效应，其实还是可以用电路学的关系式就可以来去决定。好 ，Alright, so here's the condition for quasi-state approximation. However, you should ask, so the expression says it's L, the size of the structure must be much smaller than 1/6 of a wavelength. How much smaller is much smaller? Okay? Now, so that's interesting. Say if I have a structure of lambda over 20, 1/20th of a wavelength, do you agree that this is much smaller than 1/6 of a wavelength? 同意吗？好啊，同意了哈。基本上我大概抓这样子啦，1/10个浪达，我们就算它极小了哦。虽然其实有点牵强，好不好？有一般原则了，好不好？我们就抓1/10个浪达哈。虽然严格来讲，1/10个浪达不是真的那么小，哈，但这一个。但因为我们在电磁学里头，其实1/10个浪达大概是我们常能够接受的一个标准哈。为什么这样讲 ？So, what is the significance of a wavelength? What is the physical phenomenon associated with one wavelength? One wavelength suggests that the phase will change 330 degrees. Or in other words, the vector, the signal, the vector that represents the signal shall rotate its orientation by 360 degrees in one period as it travels for one wavelength. So if there are two vectors differ by 90 degrees, would you agree that the two vectors are the same? 你可以说这两个向量相同吗？我想你应该没办法接受吧。好，那你看这个是差多少？差1/4个浪达，对不对？好，差1/4个，差90度。好，那 how about that? If the two vectors of the same magnitude are differed by 45 degrees, that is 1/8 of a wavelength. Would you accept that the two vectors are the same? No, probably not, right? How about this? 20.5 degrees. Well, when we treat electromagnetic problems, well, the usual criterion to say that the two vectors are largely the same, 大概相同哈，两个向量大概相同的话，假如它们的相位差在22.5度以内，事实上也是1/16个浪达，大概是可以接受的。好 ，OK。Alright, so one thing you should memorize is this. Yeah, from my own perspective, I usually remember this criteria, or yeah. That's the limit for determining whether or not the quasi-state approximation is valid. So what happens for frequency beyond the quasi-state limit? That is, the component, which is an inductor at low frequency, can become a capacitor, shall show different properties. For example, what do you know about a battery? What do you think of a battery? Can battery be approximated with an inductor or a capacitor? Well, in general, we usually model a battery as a capacitor, right? With a large capacitance because it stores a lot of electrical charge in it. However, as the frequency goes up, the impedance of a battery shall change from capacitive into inductive. And if you continue increasing the frequency, then the impedance of the battery will change from inductive into capacitive again. So as the frequency goes up, as the frequency varies, a component shall change between inductive and capacitive property alternatively. 所以我这边才讲说见山不是山嘛，就是说低频的时候，我们通常讲电感跟电容，指的是这个元件在低频的时候所产生的、所出现的特性。但这些特性在频率够高的时候，你会发现，从刚刚的那些式子去看它的 higher order term， 那些 higher order term 在频率够高的时候，它会越来越重要，它的那个数值会大过于 lower order term 所以本来的电容元件在高频的时候会变成电感，频率再拉高它会变电容，再拉高它会变电感所以这个是我们在看电路特性的时候，其实要留意的是，它其实是跟你观察的频率有关Alright, so to further investigate the condition of quasi-state approximation, we have recognized the equation can be written in this form, which shall approximate to L much smaller than lambda over 2 pi, which is around 1/6 of our wavelength. And lambda is the wavelength corresponding to velocity and frequency. And anyway, the result suggests that the length of the structure must be very small compared to the wavelength so that the quasi-state approximation is valid. Alright? Okay, so now let's move on to the other topic, which talk about the so-called electrical field system and the magnetic field system. 电路系统跟磁路系统所以顾名思义 electrical field system, the dominant field within an electrical field system is electric field, and vice versa. So for electrical field system, the electrical field is the predominant factor. So a simple example is if you have a capacitor, it is an electrical field system, all right? And if you have an inductor, so it falls into a magnetic field component, all right? And so let's examine our figure 5.19 again. We know that it's an inductor, so it falls into the category of magnetic field system, because for the static case, the only field appears within the structure is the magnetic field H. So you have Hy sub 0. So this is the magnetic, the predominant term in this structure. However, we know that if you have a time varying current source applied on this structure, then Hy sub 0 will become time dependent. So the derivative of Hy sub 0 is non-zero. So non-zero derivative of Hy sub 0 will brings up what? Brings up Ex what? The electrical field. Electrical field. So let's think. So the quasi-static magnetic field gives rise to a time-varying electrical field and the corresponding displacement current. So here, beginning from this relationship, we know that the electrical currents introduce magnetic field. And if the magnetic field is time-dependent, is time-varying, it will build an electrical field. Consequently, the time-varying electrical field should produce magnetic field that is Hy2. However, if the magnitude of this thing is too small, if the time derivative of the electrical field is too small, then this term is small as well, then we can neglect it. So that is the essential part of quasi-static approximation. All right? 所以注意一下我的那个 remark 啦，也就是说，当你的一次性电场，虽然说一次性电场会带出所谓的这一个 term， 这大家还记得它叫什么吗？这是真的电流嘛，可以是 combustion current 或 convection current， 这个东西的效果是什么？等于电流。所以它叫什么？叫 displacement current 所以在等式子的同样都在式子的等号右边呢，它的物理意义都是相同的，都是电流。那这个对于电流 displacement current 假如不是很大的话，那么它所对应产生的磁场，二阶的磁场就可以被忽略不计所以这个是平板电感的结构。Likewise, if the structure is changed to an open circuit parallel plate, then it becomes a capacitor, as you can imagine. If you apply a voltage source at the left-hand side, then the voltage built up at the two plates shall produce an electrical field. Then the dominant term in this structure becomes electrical field. Then this structure is referred to as an electrical field system. So the presence of the charged capacitors, the voltage source shall establish electrical charge on the top and bottom plate. So you have charge. The charge will produce electrical field. So electrical charge is the source for electrical field. That is Ex sub 0, the fundamental term. And if the voltage source becomes time varying, become an alternating source, then Ex0 becomes time dependent. Then this time varying electrical field will produce displacement current in this equation. So this displacement current will have its corresponding magnetic field, Hy1. So the two together forms the quasi-static approximation. And if the Hy1 term is not large enough, then the time-varying magnetic field, this is supposed to be what? Minus del B over del T, right? But if the time derivative of this thing is not big enough, then the Ex2 term is not large enough and can be neglected. So this is the electrical field system. All right, then let's look at this structure again by consider that the medium between the plate is conductive. So supposing that the material inserted between the two plates is not a conductor, is not a of metal, okay, it's a dielectric, but with some small conductivity. 所以我们可以把它想象成是一个不是那么好的绝缘材料。也就是说，在这一个介链材料里头，它有一点点的导电性。那这些一点点的导电性，其实就会产生漏电流，产生传导电流。那这个时候呢，你的状况就会比较好玩，因为它在加上这一个讯号源的时候，就会同时有一次相的电场跟一次相的磁场，事实上是零次相的电场跟零次相的磁场。然后这个零次相的电场跟磁场，只要让它讯号源有时间变化的话，就会带出一次相的电场跟一次相的磁场。这边推导有一点点不能讲复杂啦，但请你要 pay attention, okay? Alright, so let's consider the two parallel perfect conducting plates with an open circuit at the end. So this is fundamentally a capacitor, parallel plate capacitor. However, the material in between has a conductivity, sigma. So if we apply a voltage source from the left, then what happens? It will establish electrical charge on the top and bottom plane. At the same time, it will produce a conducting current. And because the conducting current is driven by the voltage source, so you will have zero order electrical field and zero order magnetic field at the same time. So let's see the zero orders term. Okay, so first is the electrical field. Supposing that this voltage source is a DC source, V sub 0, then the electrical field is determined by the size, the magnitude of the voltage over the distance of the parallel plate D. And the conduction current can be found with this equation. J, the magnetic field, the field intensity is proportional to conductivity and the driven electrical field intensity. So substitute the expression for E into this expression, you get the current density, sigma V sub 0 over D. So, and what is the direction of J? Well, it's from top to bottom plate if the voltage applied to the left is positive. And this, note that this red arrow should show up everywhere in this parallel plate structure evenly. 注意因为上板到下板的电压 V0 是一样的，所以在这一块结构的中间，这一个红箭头由上到下的电流是均匀的，可以吧？好，但再想想看，假如说在这一个结构当中，每一个地方都有从上到下的红色箭头，那么这些箭头、这些电流是从哪边带来的？从 voltage source 啊，对不对？从哪边流过来？从左边流过来，下来之后才从右边流过去。那你想一下，这一个电流的分布在空间上的分布会长什么样子？好，好，等一下下一页再看好 ，OK。So let's check out with the Ampere's Kirchhoff law. That is, if you have a static source, then the current JC, conduction current JC, is driven by sigma times E, and that should produce the magnetic field. You see that the spatial variation of magnetic field is proportional to the current density. So again, to derive the expression for Hy, we do the integration over Z. So we end up with this thing, Hy equals to blah, 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 like this. And of course, there is a constant C1. However, as we already know, it can be solved using the boundary condition. Again, this is the, you should put one number over here. 0, Hy 0. Why? Because this expression, this magnetic field, has no dependence on omega. So it's a zeroth order term of omega. So it has 零次项, all right? And the boundary condition helps us determine the constant C1, all right? And we should look at which direction? We should look at to the right, over here, all right? The constant C1 equals to 0 because Hy at Z equals to 0 equals to 0 in view of boundary condition that the surface current density on the plates must become 0 at Z equal. 有没有看懂这一句话？可能一下没看懂哈，没关系啦。我们刚才讲的什么？这边是从上到下的红箭头。虽然它是均匀分布的但它是从左边进来，然后下来之后从右边收回去。So here I try to draw this red arrow in terms of different widths to signify the amount of currents at the different place of the parallel plate. So as you can see, the current is larger to the left and becomes smaller and smaller and should become 0 at the very right end because, well, you don't have a conducting plate in this structure. And you know that there are crosses over here. What are the crosses? Well, they are the magnetic field. And here's a question for you. What currents produce the magnetic field? Is the magnetic field produced by currents going from top plate to bottom plate, or is the magnetic field produced by current goes from left to right? 来自己考验一下自己这些叉叉是谁产生的？是由上到下的电流，还是由左到右的？手可以比一下用手比一下嘛假如你想的是由上到下的电流，这当然是很自然的想法嘛对吧？那这个你要想你假如是由上到下，这边是叉叉，这边呢点点，这边是叉叉，这边是点点，然后这个箭头都是一样的，所以垂直方向的电流所产生的磁场，在这个空间中其实是在这个方向上面其实是这样互相抵消的。所以这个叉叉磁场来自于什么？来自于上板的电流跟下板的电流。然后右手比一下，上板的电流叉叉的嘛，下板呢，下板就绕回去，所以也是叉叉，所以它不会被抵消。然后因为电流这边大，这边小，所以这边叉叉多，这边叉叉少。OK， 所以这告诉我们这个磁场来自于 conducting current 的磁场，它虽然是 omega 的零次项，但是它有 z 的 dependence 所以在这个 plate 的左边跟右边，它的磁场强度是不一样大的，靠左边比较大，靠右边比较小，可以吧？因为上面的红电流在左边比较大，在右边比较小。Okay, so even though you see that the electrical field is the Ex sub-zero term is homogeneous. Is homogeneous at every place within the capacitor structure. The Hy sub-zero term, which is also the zeroth order term, but it's a function of z. It's a function of z, which is larger to the left and smaller to the right because the current that produce the magnetic field, the current J is larger to the left and smaller to the right. Right? So beware about the remarks. Okay, so next is applying the voltage source. So suppose the voltage source is a sinusoidal one, so V can be replaced with V sub 0 cosine omega t. And the corresponding zeroth order term becomes time dependent, which both of them are coupled with cosine omega t terms for the E sub 0 and H sub 0 term. Then what happens? Well, let's try to derive HY1 term and EX1 term. So what produces HY1? The time variation of EX0. What produces EX1? The time variation of HY0. Okay? Now, so it's quite straightforward as we have done before. The time variant zeroth order electrical field produces the first order magnetic field using this equation, and the time variant magnetic field produces the first order electrical field, as this equation suggests. So let's go to the next slide. So because we have the same structure geometry, so the EX sub 0, the time variant EX sub 0 produces the HY1 term. And here, again, we use the so-called phasor representation. So we don't have to explicitly 什么明显的、明确的把它写出来。We don't have to explicitly write up the cosine omega t term. We know that this is a sinusoidal function, so we use this bar to represent this as a sinusoidal signal. Okay. So HY1 is produced by EX sub 0, and the HY1 term after the integration is this. So you have a constant C2 to determinate. You have another constant C3 to be determinate for EX1, which is derived from HY sub 0 term. So here we say they are the first order term because they have one first order omega dependence in both terms. However, the spatial dependence of HY1 is Z only, but it's Z to the square for EX1 because the father, okay, the parent of EX1 is this equation, is this term, which is also a spatial dependent term, okay? All right, to determine C2 and C3, we should apply the boundary condition. So again, for C2, the boundary condition is located to the right. We know that there is no currents at the right end. So for HY1, C2 should approach to 0, should be 0 for the HY1 term. On the other hand, to find out C3, that is the voltage, the electrical field of Y1 term, we should look to which direction? We should look to the left. That is the location of the voltage source. As I already mentioned before, the voltage source is the what? Is the constant voltage source, which means the voltage at the two ends, A and B, is a constant number. It can only be changed by EX0, the higher order term, EX1, EX2, EX3, cannot change this value. So the boundary condition is for higher order electrical field term, EX1, EX2, EX3, they should be 0 at this position, Z equals to minus L. All right, so by substituting the boundary condition for EX2 term, that is, if you take in the line integral on the left end, the voltage should be what? Should be 0 at the left end. So if you substitute the expression for EX1, you end up with this expression, and you can find out C3, which are a little bit complicated. But anyway, it's still derivable. It still can be computed. So you just need to know which way to look into to find out the boundary condition. 所以以这个结构来讲，磁场的 boundary condition 在右边，电场在左边。因为右边是开路的，所以那边不会有电流；左边是定电压源，所以它的高阶电场不可以存在。不然它会有额外的电压加在左边，是不合法的。Okay, so here we have the expression for EX1 and HY1. That is the first order term. So are you happy now? Well, if you look at the problem a little bit closer, you find out that the EX1 term is an electrical field. And if you have an electrical field applied on a conducting material, you should have what? You have a conducting current. So the presence of EX1 will again produce another current. And this current will again produce a magnetic field. So we have the so-called complementary term now, HY1 的补充项。我不知道它后面是用 prime 还是用 C 啊？我不晓得，看看。So the presence of EX1, because it appears in a conducting material, so we should have the supplement term for magnetic field intensity. So you will have HY1. So now that HY1 comprise the term due to time varying electrical field, and which is 我这样写了HY1 的贡献成因主要是来自于时变的 EX0， 但是 EX1 本身也会产生 HY1， 所以它产生的是 HY1C complementary term， 所以这是这个问题比较复杂一点的地方。Alright, so here's the derivation for the supplement term for HY1. So it's produced by the conducting currents due to the presence of EX1. So we simply apply the expression for EX1, as you have seen here, and the term is, again, we need to do the integration over the z direction. So you have another C4, another constant C4. The constant C4 is 0 for the same reason that C2 is 0. So you look at to the right, because there is no current at the right end, so C4 equals to 0 as well. Alright, so here's the complete expression for HY1, which contains two terms. One is from time variant EX sub 0, and the other term is due to the presence of EX1. Note that the frequency dependence of HY1 are omega for the first term and omega for the second term. So they fall in the category of first order term. Alright? However, the spatial variation, spatial dependence, Z, is quite different for the two terms. Alright? 所以我们下面有注解了这一项是来自于 EX0 时变量的位移电流，这一项呢是来自于 EX1 所驱动的传导电流，好不好 ？Okay, so if you combine the zeroth order and first order term for electrical field and the magnetic field, you end up with the two expression. Alright? It looks a little bit scary right now. Alright? Agree with that? And you've combined them together. If you combine them together, or if you use the magnetic field to write up the relationship between I and V. So here is the current and voltage relationship. If you can substitute the hy sub 0 and hy sub 1 term together to have this term. And what I'm going to do. So what is the relationship of I and V? I over V is what? Y. 这个叫什么 ？admittance。那你叫是 V over IA 等于什么 Z？ 叫什么 impedance？ So I'm trying to derive the expression for admittance or impedance. So in this slide, it tries to write up the expression of this in terms of admittance. So it's defined as the ratio of current over voltage. And you can do it yourself to write up this expression. Here we use another approximation, not that this is equal. So this is the analytical expression for the admittance. However, it becomes double tilde, so it's an approximation. What we have is use the relationship that this is a small number. This is a number much smaller than 1. So if this thing is much smaller than 1, then this approximation is valid. So by using this relationship, the things in the denominator goes into the denominator. 所以那个小数的那个趋近啊，也就是那个1加巴拉巴拉巴拉那个1减 j omega 这个，假如说这个东西很小的话，那它可以用红框框的那个趋近式去表示，这样它就可以把它从正1变成是负1把它变成是在分母。那为什么要把它变成分母？因为你可以 identify you can identify this thing is what? This thing is capacitance. This thing is what? This thing is conductance. This thing is what? This thing is the admittance, inductance. Alright? So if you identify the parallel plate structure for its equivalent capacitance and inductance, you find out this thing becomes the capacitance, this is the resistance, or the inverse, the inverse of conductance, and this thing becomes inductance. So you find out that the current over voltage relationship can be substituted with equivalent capacitance and inductance of the structure to express them like this. And more interestingly is if you try to draw the circuit, you end up with this thing. You have a capacitor in parallel with another line with which is a series of a resistor and inductor. However, the inductance of the inductor is only 1/3 for this parallel plate structure. So what is the significance of this result? What is the badass in this picture? What is the bug in this picture? The bug is this resistance, which is due to what? Which is due to the conductance in this dielectric. 因为这个结构，它中间塞了一个介电材质，但是用料不好你跟奸商买了用料不好的介电材质，它有漏电流，所以那个漏电流呢，造成了电导。那你当然也可以把那个电导用电阻来表示。而这个电导就会产生额外的电感特性，所以它变成是把电感的特性带进来了。所以当你频率够高的时候，这整个电路它包含电容也包含电感，所以它的电感特性在高频的时候就会跑出来那你假如没有漏电流也就那个 conductivity 拿掉的话，它就变成是一个 单纯的电容，好不好？很棒，对不对？但假如你的那个电导不等于0的话，你的电感特性就会跑出来。那你现在问的是，为什么你的电感特性只有1/3个 L？ 为什么不是1个 L？ 为什么？为什么只有1/3？为什么？因为你只要回去看你那个结构的时候，去看它的电流哈，它不是一个完整的电感啊，完整的电感后面要有一个导电的板子嘛，才是一个完整的电感，它后面没有，所以它那个电流分布是左边大右边小，所以它是一个残缺的电感，好不好？所以它的那个电感特性只有在左边比较有发挥出来，右边就没有了啊，所以你会看到它只变的是1/3，好不好？这个部分内容其实还蛮有趣的哈，回去看一下。